Maximum likelihood estimation, MLE, is a tool we use in machine learning to achieve a very common goal. The goal is to create a statistical model which can perform some task on yet unseen data. The task might be classification, regression, or something else, so the nature of the task does not define MLE. The defining characteristic of MLE is that it uses only existing data to estimate parameters of the model. This is in contrast to approaches which exploit prior knowledge besides existing data.
We have samples x1 and assume that given they come under distribution associated with parameters of theta. We know the form of distribution, but we want to know the parameters of distribution. For one dimension, estimate parameter with the assumption that the distribution is normal Gaussian variant. We need to know which Gaussian distribution is more likely represents the data.
Assuming that the data is independently sampled, now problem is to find maximum of theta. The probability of drawing value ehon k s of I from the distribution function ehon f of ehon k s on theta is ehon f of ehon k s of I on theta. The probability of drawing the following vector of two observations ehon k s1, x2 from the distribution is function ehon f of ehon k s on theta is product of function ehon f of ehon k s1 on theta and ehon f of ehon k s2 on theta. We define the likelihood function of ehon n draws ehon k s1 x to point x from a model or distribution function ehon f of ehon k s on theta as ehon l.
This product terms are converted to addition with the help of log, which gives you maximization problem in terms of sum of log terms. We want to find mu and sigma by differentiating with respect to mu and equating to 0. Same thing we can do for variant and differentiate with respect to sigma and equating to 0. Finally, this is how we got to sigma.
Let's load the library from NumPy, Matplotlib, SciPy, Pandas, MPL toolkits, stats models and IO libraries.
Interested in estimating the number of billionaires in different countries. The number of billionaires is integer valued. Hence we consider distributions that take values only in the non-negative integers. This is one reason least squares regression is not the best tool for the present problem, since the dependent variable in linear regression is not restricted to integer values. One integer distribution is the Poisson distribution, the probability mass function, PMF, of which is.
We can plot the Poisson distribution over Y for different values as follows. Notice that the Poisson distribution begins to resemble a normal distribution as the mean of Y increases. After loading billionaire data using a histogram, we compute the distribution of the number of billionaires per country, number of billionaire, in 2008.
The dependent variable, the number of billionaires WAO in country A, is modeled as a function of per capita population. Hence, the distribution of WAO needs to be conditioned on the vector of explanatory variables L and Ks. Standard formulation, the so-called Poisson regression model, is as follows.
We can see that the distribution of Y
In our model for number of billionaires, the conditional distribution contains 4 parameters that we need to estimate.
if Y follows a Poisson distribution with equals 7.
We'll use the Poisson regression model in stats models to obtain a richer output with standard errors, test values, and more. Stats models uses the same algorithm as above to find the maximum likelihood estimates.
Stats models uses the same algorithm as above to find the maximum likelihood estimates.
Our output indicates that GDP per capita, population, and years of membership in the General Agreement on Tariffs and Trade are positively related to the number of billionaires a country has as expected. To analyze our results by country, we can plot the difference between the predicted and actual values, then sort from highest to lowest and plot the first 15.
Please subscribe to my channel and click on the bell icon to get updates of my live videos.